Thank you very much for the introduction. I realize now that I forgot to put my name in the first slide. Yeah, I'm sorry. Yeah. So this is probably why you've asked this morning. So sorry, I do apologize for
PhD record, right?
Yeah. So first of all, I'd like to thank the organizers for giving me the opportunity to speak in front of you. I know I'm going to be probably very boring, but I'm going to try not to be. And I just want to highlight that 3 years ago, I've been in Vienna at the conference, and I was just sitting there and watching the presentations. And I'm really happy that now I can be in front of you and presenting some parts of my stuff. So my title is quite long and quite complicated, I think. So I would like to split it into 3 parts. So basically, I'm doing the homogenization problem. So I'm combining some materials with other materials, and I'm using a mathematical model to describe this. So I'm gonna be putting cubic microlattices, and we're gonna try to see what do I mean by these cubic microlattices into nematic liquid crystals. You've already sort of seen some ideas about them, and I'm going to use them as a model to describe them. So this is essentially my outline. I'm going to be a little bit boring, and I would like to introduce some notions about nematic liquid crystals, because I believe that not everybody from here is actually working with nematic liquid crystals, and maybe I'm just going to recover or review some information also about the Landau-de Gennes model, which is going to be useful in the end of my talk. Then I'm going to present you what do I mean by these cubic microlattices. And then I'm going to present the setting for the homogenization problem. And then, of course, the main homogenization result. And then I'm going to talk a little bit about some sort of rate of convergence, so how fast those things are going to what we want. And then I'm going to make some particular choices, and I'm going to look at the Landau-de Gennes model and see some particular cases which are somehow interesting from my perspective. And in the end, I'm going to talk a little bit about future work. So I'm going to be a little bit boring about nematic liquid crystals. So I would like to, this is an image that I have from Jamie Michael Taylor, and I've kind of adapted it, and I've put this line of temperature here. So let's just imagine for a second that we have a material for which its particles have this elongated shape, as you have probably seen before. And we all know that, okay, in the solid crystal, everything is aligned, everything stays nice and perfectly, in the sense that it stays nice from the positional perspective. So the center of the masses of each particle form a lattice, and also we have an orientational ordering, meaning that all the particles look in the same direction. Now, in the isotropic liquid state, we expect to have none of this. We have chaos, everything looks in every single possible direction, everything moves. So in the nematic state of matter, we have still no positional ordering, meaning that the particles can still translate freely, but we have some sort of orientational ordering. So locally, the particles would tend to look in the preferred direction. They do not necessarily form layers as smectics, as you have seen in the presentation of Giacomo on Monday. So we're only be talking about nematic liquid crystals in here. And today I'm also going to be focusing only on thermotropic liquid crystals. So the materials that can enter this new state of matter by varying the temperature. There are also lyotropic ones in which you can change the concentration of particles and so on. But today, only thermotropic liquid crystals. And I've said that, okay, I'm going to use the Landau-de Gennes theory. Okay, so a few applications you probably all know: liquid crystal display technology. We have a big LCD here, and our phones have plenty of them. But I wanted here to highlight some very simple examples of liquid crystal technology, like the alarm clock, the digital thermometer that I would use in my car because it's quite old, and I would install it externally, and something that you can find in Eastern European countries, which is the exchange rate board inside of each bank when you go and change money from your Romanian lions to euros or dollars or whatever. But most of them use the very simplest LCD technology, US dollars, okay. Most of them use the simplest LCD technology in the sense that the unit of image, the pixel, is quite big. So it's not our phones. We don't have a huge resolution, and we only have just one color. We don't have 1 million colors. Okay. So do materials like this, like the nematic liquid crystal that I've been talking about, do exist? Well, yes. And one is this MBBA, which has a really long and complicated chemical name that I'm not going to try to pronounce. But it has this chemical representation, and it seems like for some people, this representation actually means that the molecule is elongated. For me, it still doesn't say anything, just CH and a bunch of N's. But the reason why I want to present this material is that it can enter this new state of matter only at temperatures between 21 degrees and 48 degrees Celsius. And now let's make another exercise of imagination. Let's just imagine that our phones are made with MBBA in a pure form. Now we would have some issues when we would go outside right now because it's less than 21 degrees Celsius. Or even inside, of course. So our particles would enter the solid state and we would lose all the optical properties and we would stop seeing our display. At the same time, if we like to play games on our phones, everything is super connected and we have CPUs and GPUs which generate heat locally. Therefore, parts of our liquid crystal display would stop working. We would see the isotropic liquid state. So already we can see a desire to create a new material by some sort of homogenization process in which we change the range of temperatures. Let's just make it from -50 to +200. And in this way, we are sure that we're not going to have issues using the material. Okay, so now let's go into the details, the mathematical details. So I'm going to be talking a little bit about Landau-de Gennes, so the mathematical models that I'm going to be using. So let's just imagine we have a container which is bounded and smooth in 3 dimensions. And at each point, we define a probability density function, which is going to tell us what is the probability for a particle to look in a specific direction. So before we had an n, which was telling us the particles want to look in that direction. Now we just have a probability density function, and we just say, okay, the sum of all probabilities is equal to 1. And we introduce this ordered tensor as a difference. So because we have the head-to-tail symmetry of the particles, if one were to compute the first order moment associated with that probability density function, you would see that it's 0. So the first order moment, which encaptures some sort of properties of the alignment of the particles, is the second one. And we actually measure the deviation from the isotropic state of matter, because in the isotropic state of matter, the probability density function is constant because all particles want to look in every single possible direction. So we are going to be working with Q-tensors, and we're mainly going to be seeing them as real matrices which are symmetric and traceless. So our objects are going to be these. So in here, we are usually interested in studying critical points of free energy in which we have 3 components. So we're going to have some sort of elastic energy, which is going to tell us how the orientations of the particles deviate or they have some sort of distortions throughout the space. Then we're going to have some sort of bulk energy, which is going to tell us the internal properties of the material that we have chosen. And then a surface energy, which is going to tell us how the particles want to align or some sort of interaction with the walls of the container. Now, let's see what sort of possible choices do we have for these elastic energy, bulk energy, and the surface energy. Well, the typical choice for the elastic energy is this expansion in which we have 3 constants there, L1 and L3, and we have some inequalities such that, okay, we expect to have some partial derivatives of the Q-tensor that we use. And then, of course, we have the more simpler format in which we only use the gradient of Q squared, the one constant approximation. Now, for the bulk energy, I would like to stop at the typical choice from the Landau-de Gennes, in which we use 3. I mean, we have a quartic polynomial in Q, in which the coefficients that we have depend on the material that we have chosen. More specifically, the coefficient of trace of Q squared, this A, is temperature dependent. So it has this form, and this T is the absolute temperature, and T star is the temperature at which we have to transition from the nematic to the isotropic state. So, okay, there are also other simplistic choices for the bulk energy, which are not really loved by mathematicians. But this might work in some sort of paranematic regime, so only a quadratic polynomial in Q. And for the surface energy, I just want to highlight the most familiar one, Rapini-Papoular surface interaction in which if one were to minimize only this surface energy, essentially Q is going to want to become this Q mu, which is a Q tensor defined based on the outward normal of the surface of the container that we are using. So Q is going to want to become Q mu, and this constant in front of it is called the anchoring strength. And at the same time, we can introduce some sort of surface energy, which is similar to the bulk energy that we have seen here. So we had a polynomial in Q, a quartic polynomial in Q. We can introduce in the same fashion here some sort of surface energy. And now that we have seen those choices, we can actually discuss the mathematical motivation of what we were discussing before. We want to create new materials in which the range of temperatures is now different. So in order to do that, we put this question. The only part in which we have seen something which was temperature dependent was the bulk energy, in which we had that coefficient A. So we put ourselves the following question: can we achieve through colloidal homogenization? So we're placing some particles inside of the nematic liquid crystal such that in the end we get the new material, but with different coefficients, with different properties. And the answer to this question is yes. And it's based on previous work done by Giacomo Canevari and Arghib Dani-Zărnescu, which are in the room. And their initial article, in their case, they've chosen, the easiest possible setting. We start with some spheres, right? The colloids that we're placing inside of the nematic liquid crystal are spheres, and we analyze whether the homogenization process can take place. And the answer is yes, sorry. And their setting was the following. So the distance between each two spheres that they have chosen is epsilon, where this epsilon is the homogenization parameter that we're going to be using. And the radius of each sphere is actually epsilon power to the alpha, where alpha is just an exponent bigger than 1. So essentially the radius of each sphere is smaller than the distance compared to the other spheres. And yeah, I think I'm going a little bit too fast, but nevertheless, in my work, I have chosen a completely different configuration, which is called a cubic microlattice. And as you can see, it's a little bit different from the following sense. So initially, in the article of Giacomo and Arghib, what they've done was to choose a union of disjoint particles. So everything was quite far away, and everything was not connected. So in this case, I've decided to start in the same fashion as they did. So we start with the black boxes that we have there, placed in the same periodic fashion as the previous case, but now we have interconnected them. So now the colloids are just a big particle. It's not a union of many disjoint particles. It's just one big particle. And we try to mimic the same configuration. So the distance between two black boxes is epsilon dependent, and the size of each black box initially is somehow dependent on epsilon power to the alpha, and alpha is between 1 and 2. Okay, why do we have the upper bound for alpha? That was a very technical issue. Essentially, if you take alpha to be bigger, your energy might be unbounded from below. So it's a very technical result why we have chosen alpha to be bigger than 1 but less than 2. Now, the reason why I've chosen such a configuration, so the cubic microlattice, is because it's being used in industry. So it actually looks like this. So the picture is not mine. This is a picture taken from the article of Serra and collaborators. So as you can see, it tries to, this is the real cubic microlattice, which is called bistable porous solid matrix, I think. In their article, they're actually analyzing something more. So I would like to highlight that they were analyzing memory effects and bistable pixels. So by using this colloids, they've actually seen that locally some particles remained aligned even after we've stopped the electrical field. or the current applied to the display, which might be actually interesting if you try to think about the exchange rate board that I've shown you previously, because on that case, we don't need to actually show the same image every single time. We have the exchange rate for 1 day. So maybe, you know, we put the current there, we change the orientation of the particles, and then we take out the current, the electric current, and maybe the particles are going to stay in that way, and we're going to see the same image throughout the day. But my talk is not, I mean, I'm not in, I mean, I didn't study anything related to memory effects. I was interested only in the homogenization process and proving essentially a gamma convergence result. Okay, so now that we have seen that these particles exist and they are being used in the industry, let's discuss a little bit more, because I want to highlight the fact that the black boxes that you have seen previously, they I've chosen them to be, I mean, not necessarily cubes. So they might have different lengths, and this is going to become interesting in the last part, because we're going to have some sort of new term appearing out of nowhere. So the other interconnecting boxes, they look in this following way. So they are stretched in every single direction of the coordinate planes that we have chosen. And at the same time, I want to highlight that the black boxes, they are black or gray because most of them are the interior. You cannot see them, right? I mean, if we were to move at this picture on the left, the only black boxes that we can see are on the outer boundary of the cubic microlattice, the ones which are inside. They're not actually in contact with the nematic liquid crystal. I want to highlight once again that this particle is just a polymer. This is a plastic that we put inside the nematic liquid crystal. It's like this scaffold that we have here, which keeps the projector, and the air passes through. So the air is the nematic liquid crystal. The scaffold is the cubic microlattice. So we are actually able to prove that the contribution from the surface energy from the black boxes is actually irrelevant, because the amount of black boxes which are actually in contact with the nematic liquid crystal are quite small and few, so they don't count. So we don't care about them. So the only thing we care about are actually the interconnecting boxes, and those are actually, they have only 4 faces in contact with the nematic liquid crystal. Okay, so I've also wanted to highlight here what's happening when the homogenization parameter goes to 0. So the cubic microlattice becomes thinner and thinner, but also denser and denser, because on the right I have a zoomed in picture. Okay, and as this epsilon converges to 0, the volume of the scaffold actually converges to 0, and we call this the dilute regime. But at the same time, the surface area of the cubic microlattice explodes. So let's go more into the details, the mathematical details, because we were discussing about Landau-de Gennes. So let's see which is our setting. So again, we start with the container in R3, which is smooth and bounded. So we don't care actually about the container. We denote n epsilon as being this cubic microlattice, which is epsilon dependent that you have seen. And omega epsilon is going to be the region filled with nematic liquid crystals, the air which is surrounding our room. And because we're not interested in what's happening next to the boundary of the container, we just, you know, impose some Dirichlet conditions. We take a h1/2 function and we say, okay, we define these spaces and we're going to work with them, because we don't care what's happening next to the container. We only care about the homogenization process and next to the cubic microlattice. So what is our energy that we use? Well, again, we have 3 components. We have an elastic energy, a bulk energy, and some sort of surface energy. And we have placed in front a coefficient which tries to control the fact that this surface area explodes as epsilon goes to 0. So at first, this is not randomly chosen. Okay, maybe some can argue that this is somehow artificial. Razvan, you know, why have you put this? Okay, but I mean, this, at some point, we're just trying to control the fact that the surface area explodes, and at the same time, I mean, you can see this as just going into the surface anchoring strength that you can choose in the surface energy density that you can choose. And once again, you can see I haven't specified which is the elastic energy, I haven't specified which is the bulk energy or the surface energy, because I want to play and choose as many possible in the end. So what do we expect in the limit for the homogenized energy functional? Well, we expect to see no surface energy interaction, right? When we put sugar into our coffee, we don't want to see the sugar. We want to feel the sugar in our coffee. So this is exactly the same idea here. We don't want to see the cubic microlattice after the limit. We only want to see some sort of an effect. So this homogenized effect, we would like to be in the same form with the bulk energy that we have started with, such that when we add those two together, we're going to get a new bulk energy. Okay, so as I said, I don't want to choose yet the elastic energy or the bulk energy or the surface energy, so I impose some general assumptions on it. Okay, for the elastic energy is differentiable, strongly convex. For the bulk energy, we assume it's continuous, bounded from below, and we have a sextic growth. Because we work in 3D, we work with H1 functions, we have the compact embedding into L6. So, I mean, we were lazy in some way, but we've chosen the simplest setting in which we can actually prove the gamma convergence result. For the surface energy, okay, we say it's continuous and we have some sort of quartic growth. And now that we have said, I mean, we have put the general assumptions, we can present the homogenized functional, because we haven't discussed about what is this homogenized effect that we have. Well, because earlier we were discussing about the fact that for the interconnecting particles, we only have 4 faces in contact with the nematic liquid crystal. Therefore, we're going to expect to have in the limit some sort of sum of integrals in which we integrate over the faces of a cube in the direction of x, y, and z. And those P, Q, and R, once again, those are the parameters that we have chosen for the lengths of the black boxes, which are going to basically define the whole structure that we have there. Okay, so again, if we choose, for example, P equals to Q equals to R, the homogenized effect looks very different and much more simpler. But now we can present our general homogenization result, which is the following. So if we have an isolated H1 local minimizer of the homogenized energy, then we can approximate this by a sequence of H1 local minimizers of the approximating energy, such that the harmonic extension operator applied to these Q epsilons, they converge strongly in H1 to Q0. Okay, what do we mean by this? Well, if I have a desirable configuration, I'm saying I can achieve it through homogenization in very simple terms. And okay, this is the harmonic extension operator. I'm just saying, okay, it solves Laplace inside of the cubic microlattice, and I want to be equal with Q on the walls. Now, the main difference, I mean, I'm basing this on the machinery produced by Giacomo and Artier. But the main difference here was the fact that instead of having disjoint particles, I have one big particle, sorry. So the technique of, I mean, usually when you work with extension operators, you would like to prove at some point that you have some sort of uniform bounds for the gradient. Now, in order to do that, in my case, it was a little bit complicated because I couldn't isolate the particles. Usually, I mean, if you have spheres, you can look in the vicinity, you can play around there by some reflection techniques, and everything works nice. But in our case, because everything was connected, I've actually done some sort of iterated extension operator. So first, I've constructed an explicit one, which was defined on the entire domain. But in order to do that, first, I've extended it into the connecting particles. I've got an extension. I had the desired inequality, which was epsilon independent. And then I've done for that another extension on the black boxes, and therefore I was able to extend over the entire domain. So that was, let's just say, one of the main difficulties there. But we can also discuss about some sort of rate of convergence for the surface energy. So we would like to know how fast the surface energy is actually converging to the homogenized effect. So actually, I'm discussing about rate of convergence in terms of how fast the sequence of minimizers converge to that Q0. So this is this is the surface energy interaction converging to the homogenized effect, and okay, this is the H1 norm of the minimizers converging to the other minimizer, and this epsilon is powered to the M alpha, where M alpha is essentially the minimum between those two fractions. Okay, yeah.
Let me ask you, this surface energy that you are using here is a specific one, the one which is the anchoring, which gives you the anchoring with the boundary condition that you mentioned at the beginning, or a generic one?
It's a generic one.
So for whatever boundary surface.
As long as it satisfies the general assumption that we have here for the surface energy, so the last one, as long as we have this,
Satisfied by the one.
Yeah, exactly.
Proposed.
Yeah. Okay, so I'm saying this is some sort of rate of convergence because I'm not estimating this in terms of epsilon, because that would be probably a proper rate of convergence from my perspective. Anyway, now we can move on to the particular cases, because we haven't chosen the elastic energy, we haven't chosen the bulk energy, neither the surface energy. So because we're not interested in modifying the elastic energy, we don't expect to see some sort of modifications for the distortions of the particles. We just choose one, and then we discuss more about the surface and the bulk energies. So we distinguish two big cases. The one in which we have cubic symmetry, that's how I call it, cubic symmetry, when P is equal to Q equal to R. So the black boxes were cubes, and the one in which we have no cubic symmetry. So let's begin with the simplest configuration possible. We start with cubes. So we choose the typical choice for the bulk energy. So A, B, and C. We have the coefficients A, B, and C, and we would like to transform them into A prime, B prime, and C prime. Now, in order to do that, we choose the surface energy density function to be of this form. Now, once again, one could argue and say, what do you mean by choosing? How can you choose them? Okay, there are different techniques of rubbing and coating the material such that you can make the particles stay in the way in which you want. But let's just imagine we could actually realize physically this sort of surface energy density and surface energy interaction. So in this way, we can actually prove, okay, you see, I've chosen the surface energy to be somehow similar with the bulk energy that we have chosen here. We have a quartic polynomial in Q, which was the same thing for the surface energy density. And we can actually prove that the homogenized effect has this form. So already you can compare it with the bulk energy that we have here, and we can see that the coefficients here are A prime minus A, B prime minus B, C prime minus C. And of course, when we add them together, the initial bulk energy plus the homogenized effect, those initial coefficients are going to disappear, they're going to vanish, and we're going to get the new material now with different properties. So that was the main idea of the homogenization problem, and this is the simplest setting that we can use. Okay, one can also use the more simpler version of the para-nematic regime, in which we only have a quadratic term for the bulk energy density, and we can use the Rapini-Papoular surface energy density. So we can transform A00 into A prime 00, or you can transform ABC into A prime BC if you use the Rapini-Papoular. So this is just an example.
Question. So on the previous slide, can you I think you said it before, but I forgot. What did you assume on the elastic energy? This
one.
So the value of L1, L2, and L3 does not affect the homogenized.
We work in the dilute regime. This is the crucial aspect. Therefore, we're not going to modify the elastic constants. If we
not this way, but the other way, that your output,
yes,
homogenized output does not depend on L1, L2, L3. That's what it looked like.
No, it depends. It depends because
no, in your specific. Don't go all the way. In your specific result, can you go back to forward to your specific result?
The particular cases, yeah, but I wanted to highlight here that in the free energy and in the homogenized one, I get the same elastic energy that I've chosen at the beginning. I can move to the particular cases here. Here,
Yes.
yes.
So there it looks like as if you get kind of as if the homogenized bulk and the bulk energy which arises from homogenization is completely independent of L1, L2, L3.
Yeah, no.
He's only writing a bulk energy. He's not writing elastic energy
No,
here.
but that's not dependent.
It should, I mean, boundary terms only communicate with the bulk through the elastic energy.
Mhm.
So therefore, I find it surprising that the homogenized bulk, I mean, the homogenized part does not depend on L1, L2, L3. That I find a bit surprising.
Maybe it's because of our scaling of the cubic microlattice.
Still, I mean, yeah.
All right, this is my feeling, yeah. Okay, so at the same time, you can choose more general bulk versions. So if you want to use the sextic Landau-de Gennes bulk potential, you can always use it, or you can use a more general polynomial. And at the same time, you can describe the surface energy density function in the same way, in a polynomial version, as long as you still satisfy the growth conditions that we have seen for the general experiments on the previous slides. And in this case, okay, you're gonna get the homogenized effect of again the same format with the initial bulk energy that we have chosen here. So if you choose a polynomial, you're gonna end up with a polynomial, something like that. Okay, but the interesting case that I like is the one in which we have no cubic symmetry. So again, we start with the same typical choice of the bulk energy. And we need to introduce two new parameters. So we need to introduce like a constant which depends on P, Q, and R. And we need to introduce a Q tensor A, which depends on P, Q, and R. And if we choose in the same fashion as we did before the surface energy, so we have the same polynomial A prime minus A, blah, blah, blah. The homogenized effect is going to have two parts. So the first part, it's exactly the same as in the case A, B, C becomes A prime, B prime, C prime. But we're going to get another three terms in the homogenized effect in which we have some sort of bulk energy, but we're going to have trace of A times Q squared, A times Q third, A times Q fourth. So we interpreted, we saw this as some sort of shift in the alignment of the particles. So due to the lack of the symmetry of the cubic microlattice that we are using. And yeah, those are the particular cases. So the summary is we have a homogenization result on the various general conditions. We prove some sort of a rate of convergence. For the cubic symmetry case, we can actually use more general bulk versions or surface energy densities. And the lack of cubic symmetry actually generates a shift in the alignment of the particles due to the lack of symmetry, essentially. And for future work, well, here I was, again, a little bit lazy at thinking, in the sense that my second research article was about Rugos's boundary. And of course, you have seen in the picture that this BPSM is not actually crystal clear. We don't have planes, they might have rugosity. So we could, for example, impose some sort of rugosity boundaries on the surface of the cubic microlattice and have two different length scales. So one would be for like one is going to be for the homogenization parameter, and one is going to be for the how the rugosity, how big the rugosity is. Okay, and the other future work that I'm actually interested in doing, but it's only for my inner soul and my inner peace. I don't know whether I'm going to be seeing some stuff, but lately, I mean, since I finished my PhD, I've started using two applications which are called OpenQMin and OpenViewMin, which are, you can actually visualize the configurations of nematic liquid crystal particles, and you can actually spot some defects. I haven't shown you here the defects because on the left, this is not the minimizing configuration. I haven't pressed enough the buttons, minimize, minimize, minimize. But here I was trying to replicate the case from Giacomo Canevari and Arghebdani Zagnescu, in which we have periodically displaced spheres inside of the domain. And you can actually spot the defects, and you can maybe visualize something, but it's only a visualization tool. It's not something that, I mean, I'm curious to implement the cubic microlattice in it and try to see what's happening in there. Especially with the lack of cubic symmetry case, I would like to see what's actually happening in there. So yeah, I think I finished 5 minutes early. I have no idea why, but yeah.